Hello, strange people watching this video. Today, I'm going to be telling you about vectors. So the idea for all of these videos is it's going to be targeted towards physics students, and maybe we'll get into more complex topics, but it's basically targeted towards physics students, because a lot of this stuff is not taught very formally in physics, and that always messed me up. I like to know formally what is all of this stuff. Sometimes it's just very confusing. So, today we're going to talk about what a vector is. So, okay, I'm sure you've seen many definitions of vectors in your time while studying. The first definition that you may have seen is the um, geometric definition, which that is, it's an arrow with a magnitude and a direction. That was a terrible arrow. Okay, so say this is vector A, and then let's have some sort of vector. You can have some sort of other vector B, and there are some different rules you can do with these vectors. You can scale them, and you can add these vectors. So for example, if we were to add these two vectors, you would move this over here, and you would get this. This is B, and then this is A plus B. Okay, cool. So that's the geometric definition. The problem with that definition is that it's very hard to do any maths with that, right? Um, imagine drawing high dimensional vectors, add together four-dimensional vectors and add a whole bunch of these together and do differentiation with them and blah blah blah. Obviously, this can't work forever, but it's good intuition. The second definition is the component definition. So, for example, over here, A seems to have a length of what, 1, and 1 on the y, we'll just say that. So A is just 1, 1, because it's 1 in the x direction, 1 in the y direction. B, on the other hand, seems to be, let's say, it's negative 0 point, what, 3 in the x direction, positive, let's say, 0 0.5 in the y direction. And then you can simply add them together component-wise. A plus B equals 1, 1 plus negative 0 0.3, 0 0.5, which is equal to 0 0.7, 1.5. And then that is A plus B. And then you can always go from a drawing to these and then back from these to a drawing. And so that's one definition of a vector. Now, the thing is, there are a whole bunch of really interesting theorems you could do with vectors. And and there is a more abstract definition of vector spaces that actually turns out to be very, very useful. Um, and we'll find that we get vectors of all different sorts in physics. So I'm going to give you the abstract definition, and it should be clear how it relates back to this definition here. And then we can prove some theorems in that abstract thing, and it'll apply to all possible vectors we can think of, not just these arrows, not just these component-wise vectors, but say functions can be thought of as vectors. You can have solutions to ODEs can be thought of vectors. You can have all these crazy things. So let's talk about the abstract definition. So a vector, so for the abstract definition, we're not going to start by defining a vector. We're actually going to start by defining a vector space. And then vectors are just elements inside of your vector space. So a vector space is a pair. So this is really your vector space here. But it also comes with some field F. Now, in this video, I'm not going to describe what a field is. There is a definition, and maybe I'll make a future video on that. But for now, we're just going to consider real numbers. So let's not worry about the fact that I'm saying field and this fancy thing. Let's just ignore that for now. So a vector space is just some set V. This is a set. I'll talk about what a set is in a second. and real numbers. Okay, so what's a set? A set is just a collection of items. So for example, you could have V is equal to 1, 2, 3. Mind you, ordering does not matter. But so it's just a collection of items. 2 is inside of V. You would write that as 2 is an element of V. 1 is an element of V. 7 is not an element of V. But you don't have to have numbers in here. You can have whatever you want. So for example, you could have V is equal to smiley face, poo emoji. Oh God, I can't draw that. Poo emoji and I don't know, the word hi. You can have whatever you want in your set. But this set has to come with some sort of rules. So the first thing is obviously we want some sort of addition, right? We want to be able to add vectors. As you can see up here, we can add them together. So that means in a more abstract sense, addition is just a function that takes in two vectors and spits you out another vector. Okay, so your vector space also has to come with this thing called addition. Whatever it may be, you can define addition however you really want, as long as you satisfy the following rules. Number one is closure. So this rule states that if you have, say, you, and actually I'm gonna stick with what I was using before. So if you have A and B are elements of your vector space, so for example, A could be smiley face, B could be the word hi, then when you add them together, that should also be in your vector space. So for example, maybe smiley face plus hi equals poo emoji. Maybe smiley face plus hi equals smiley face. Whatever you want, right? As long as you're going to satisfy all of these rules. The second thing you need, and this makes sense, right? Like for example, when you add vectors here, you add one vector to another vector, you get another vector. Imagine if you added, you know, this to this and you got a squirrel. That would be pretty nonsensical. So the second thing you need is associativity. I'm going to hopefully whiz through the rest of these rules. And so this one is A plus B plus C is equal to A plus B plus C. Number three is commutativity. That is the order of addition does not matter. B plus A. Cool. And the fourth one, this one is quote a little bit trickier, which is that you need an element in your set called a zero element, such that whenever you add a vector to it, you just get your vector back. So the obvious example here is just the 0, 0 vector. When you add 0, 0 to A, you just get A back. So now the fifth part, the fifth rule is additive inverse, which is for all elements in your set. So this means for all, which means for any item in your set, there has to exist. So this means there exists. There has to be some. Oh, that was terrible. Sorry, 1 second. There has to be some negative version of that in your set such that A plus negative A equals 0. So for example, maybe here we needed to require that hi is the 0 set. So therefore smiley plus hi is equal to smiley, and poo plus hi is equal to poo. Oh, sorry, that is for rule 4. For rule 5, you might require that smiley is the negative version of poo. So smiley plus poo equals hi. That might be the rule you need. So actually, maybe we can write that out. So our plus map, if it takes smiley plus smiley plus hi, and it goes to smiley. So this is your 0. And you have poo plus hi equals poo. Okay, it goes to poo. And then you can also have, say, smiley plus poo goes to hi. So therefore, hi is your 0, and these are additive inverses of each other. So that satisfies the following rules. Now, so this tells us how to add vectors together, right? The question is, you can also scale them, right? You can change the size of this, you can multiply this by say 2 and it gives you something. So we want to be able to scale them. And that's where this field comes in, or the real numbers. So the rules for scaling is this. So first of all, um, let's say alpha and beta are real numbers. In general, this might be over some field instead of just real, but we're just going to stick with real numbers for now. So you have alpha of beta times vector A is equal to alpha times beta times vector A. Okay. Then you must also have that the identity in your field, or just the number 1, must satisfy number 1 times A is just A. That makes sense. And then finally, the distributive laws, I never know how to say that one, is alpha times A plus B is equal to alpha A plus alpha B. And let's say alpha plus beta, and this is the final rule, alpha plus beta times A is equal to alpha A plus beta A. Whew. Okay, so maybe for your homework, you can show that this, so okay, abstract definition of a vector space. Let's connect it back to what we already had. So what we already had is our set V was just the set of all, two component quote vectors, right? So it's just R squared. That's what you call R squared. Or so what it is it's the set of all A, B, where A is a real number and B is a real number. So for example, pi and 3 is an element of R squared, or 1 and 0 is an element of R squared, so on and so forth. So that is your set. It's a set of all possible objects that look like this. And you can and then that is what a vector space is, right? The vector space is just all of this, along with our scale multiplication is just elements in R, and then we come with these basic addition rules. Addition rule that we've defined up here. Your 0 element is 0, 0. And you can very easily convince yourself that your standard definition that you used to here satisfies all of these rules over here. And so what a vector is it's just an element inside of your vector space, right? So here is really the definition of your vector space, and everything inside of your vector space. So for every A element of your vector space, this is what a vector is. Now, I know it seems really abstract and kind of dumb, but the really cool thing about this abstract definition of vector spaces is that there's a whole bunch of really useful theorems that we can prove about this really abstract definition here. And then you can apply that to a whole bunch of different systems. As I'm sure you'll find out if you continue doing physics, there's a whole bunch of useful vector spaces that aren't necessarily, um, just the standard thing you see here of this arrow in this direction. So some examples of that is is like tangent spaces on manifolds in GR, or you have Hilbert spaces in quantum mechanics, or really one of the most important examples is function spaces. And you can also have, say, solutions of differential equations solve abstract vector spaces. And all of these different things, you can apply theorems from this abstract definition onto those specific things. And it makes everything a lot more intuitive when you have this abstract definition. So I want you guys to mess around, come up with some wacko vector space with some wacko definition of addition. Also, I should say what multiplication is. I've kind of like ignored it here. But really, multiplication, scalar multiplication, is a a function that, takes in something from real numbers and a vector and spits you out another vector. Um, Once again, this should really be an arbitrary field, but I haven't defined what a field is to try and keep the video short enough. Thank you for listening. Hopefully this was helpful, and see ya.